Welcome to this lecture where we will discuss the steps of bioprocess design. In particular, we will focus on the first two steps, targets and specifications and data collection. Steps 3 to 5 will be covered in more detail during the rest of the week. But before we continue, it is important to distinguish between the sequence for process orientation and for design orientation. These are two different concepts. For process orientation, materials flow from the feedstocks to the purified product, and this is the logical sequence how we see the process. But the design orientation goes from the purified product, which is usually the starting point of many design projects, back to the suitable raw materials where different options may be considered. This direction can also be used for process design. And this is very much in line with step 1, targets and specifications. Here, designers define three main aspects. The goal of the bioprocess, for example, what is the target product and purity, or what feedstock is available. So we have to clearly state what the process design is for. We also need to define the desired specifications of the product. For example, the expected inputs and outputs. This helps to define the battery limits. Additional specifications may include purity of the products, scale of production, or availability of feedstocks, which depends on the local context. Constraints are also important. In some cases, there are not alternative choices, for example, when we're redesigning an existing plant or when we have to use a specific strain with a given stoichiometry. And last, we have to define the key performance indicators used for decision making and for comparative analysis. Typical KPIs refer to economic and environmental indicators like total production cost, payback period, or greenhouse gas emissions. For our case study, we aim to produce a high purity PDO from, let's say, glucose as feedstock, which is available at the factory gate, and our responsibility is to transform it to PDO at a rate of 100 kilotons per year, which is less than 10% of the expected global market. And no byproducts are assumed according to the stoichiometry from week 2. Finally, we could say that that we are mostly interested in the potential greenhouse gas emissions for decision making. Step 2 is data collection, and data inventories typically start around the bioconversion stoichiometry and around the fermentation conditions. For example, the pH, the concentrations for product inhibition. But knowing the process performance is very important too, and we can consider the TRI indicators: titer of the fermentation products, reaction rates for consumption of substrate and production of biomass and products, and the yield on the main products on substrate consumed. Let's check again how this is like for our case study. The stoichiometry was already given in week 2, from which we know concentration of substrate, pH, temperature, and nutrients requirements, and also the TRI indicators, as you can see in the bottom right corner. Now we can proceed to step 3, generate designs and redesigns. For this, let's recall the anatomy of a bioprocess where there are 4 major sections which all have different functions, requirements, and type of processes that can be used. Let's see some examples. For the first 2 sections, there are different choices for the type of raw materials. Is it first G? Is it second G? And is pretreatment needed, or only adequation of raw materials? From those 2 simple questions, multiple process options appear according to the purpose. For example, acid treatment for biomass pretreatment. For bioconversion, the type of bioreactor should be defined. It could be, for example, a bubble column, and this choice could also have consequences on the operation mode and on the reactor capacity. For the latter, it is important to know what scales have already been achieved at commercial scale, and additionally, operating conditions like the pH, temperature, and the type of microorganisms should also be considered. For the downstream process section, we should make sure that the expected quality of the products is achieved, And to do so, multiple operations could be considered, and this selection should be done based on the concepts and principles applicable to each type of operation unit, as you have seen it in week 3. Once we have selected the processing units and conditions for the different sections, we can proceed with flow sheeting and alternative designs. We will cover these points in detail in the next lecture, but for the time being, we can mention that flow sheeting is a sequential task to gradually implement more information and details in our designs. Let's see how this is like for our case study. During the previous weeks, most of the process-related decisions were made. The feedstock is glucose, and therefore limited adequation is needed. The bioreactor is a bubble column with a height of 25 meters, and the downstream process was sufficiently described in week 3. And flow sheets at the different levels will be covered in the next lecture. Step 4 is the quantitative assessment and analysis, and there are different levels that we could consider. First, the technical feasibility should be checked. For this, we use mass and energy balances, which are based on thermodynamics, kinetics, and transfer phenomena. Then, the economic feasibility could be checked, where we can estimate the capital and operating cost and other financial indicators. Estimating the potential environmental and social impacts from the large-scale implementation of the project should also be part of our activities and responsibilities as process designers. And finally, an integral sustainability assessment or a multi-criteria analysis for decision-making can provide information of the sustainability trade-offs of our system, which is also part of step 5, final designs and selection. A couple of additional aspects to consider in these steps are the sensitivity studies, since they can indicate what specific technical actions could improve the KPIs, and the context dependency for the 3 dimensions of sustainability. This is all by now. Thank you for your attention, and see you in the next lecture.